All right, so this is another example I'm just doing for you. So what we're gonna do, we're gonna set the win load, right? So win load is something we can define in the define menu, load patterns. So in the define load pattern, we can create the win load cases. So type of the win type is win load, right? No self-weight multiplier. And auto lateral load, we're gonna use it. You could choose the win SC7-16, right? SC7-16. You add this new. Where win? Yeah, wins. Why this keep? This is the window. What? This is funny. Win. Why it keep this? What is this guy? Okay, win load. What? Oh, this may be the window thingy. Okay, win load I created. So I choose ASC7-16. When you open, you see you need to fill in all the load parameters. Current wind load, wind speed is basic wind speed is ultimate wind speed. We need to meet, I think, 115 mile per hour because inside the Manhattan City, I think exposure B. I'm gonna keep it. And ground elevation factor and topographic factor, since we are in the city, no close the hill, up, uphill, downhill. I just use one default. So I think I'm ready to say OK first and close it. But now ETABS should register how to assign the wind load, wind pressure, in order to tell what we have to do. Maybe let's put it in 3D, or there are a few steps. I think I usually do it, but one example is I select all the nodes above the base point, right? And then assign a joint diaphragm here. So I assign the diaphragm, rigid diaphragm, and assign rigid diaphragm to all the node I selected. So when you when you see it, you see that D1, D1, D1 every floor. So all the nodes on the same elevation, right? They should have their own the diaphragm. Um, kind of these diaphragm actually do their own works. I will explain later. So I assign the diaphragm. I'm gonna just put this on the plan and see this is all the indication of diaphragm. So all the nodes on this floor, they tied this dashed line, black line, and this all node is tied and bounded in their diaphragm. So this is floor or this diaphragm. Eventually, we tell each this all the nodes will do some work like a ridge diaphragm, which they work ridge body motion under any lateral load. So this is actually moved together in X and Y and twist torsion, but no interior movement displacement. So this is minimum you need to set and run it. Okay. So again, you need to define your wall, right? And define the material property, section property, assign it. And you need to set up the wind load. You need to select and assign the ridge diaphragm. So you'll be able to run test run. So what I'm gonna show you, okay, first default is always show displacement under that load. I'm interested in to see overall how much wind loading is created in XY direction. I'm going to show you here in displays menu and story response plot, right? I'm going to close this diagonal. Okay. Okay. I'm going to go to displays, story, and I'm going to choose the wind load. And I'm going to choose, first of all, total story share. So here is a story diagram. This is HOMA 1. Based upon all the wind load, it helps to generate, but I'll show you where you need to double check how this steps is generate the wind load and what kind of information minimum they use. Needed. But anyway, wind loads, wind is the wind loads on number 1. There, I think wind is blowing in at global X direction, which is blue color. We show the cumulative shear forces. Total here, 2,841 cases. Total wind loading is calculate and give us the maximum total cumulative shear in X direction, 2,841. If you change the 2, this is wind loading in global 2 Y direction. Right? In the red color, you see here cumulative shear was bigger. Here 4,000, 1,111 kips. Why? Because building is wider in X direction. When you look at the plan, same thing. This. Okay. Right? When you look at this building, wind is blowing this X direction, your temperature wind is only this one. Wind is blowing Y direction, your building temperature with this is bigger. So total base shear in X direction, Y direction. By looking at this, you know which direction has more wind effect, right? By looking at the geometry, you should be able to just understand which is total wind effect is bigger, this direction or this direction. Obviously, the geometry tell you wind pressure along the height is same in X, Y, but your building width is different. So wind blowing Y direction is bigger, right? Now, associated overturning moment is obviously same, right? Because lateral effect in Y direction is much bigger, overturning moment about X, right? When it's blowing this, moment is about global X, is associated moment, overturning moment is much bigger in Y than X. That is just by looking at your building geometry. That is common sense, but you need engineering sense too, right? Secondly, looking at the overall your core wall layout. Okay, look at it. Which is stronger? X direction, Y direction, stiffer. X direction is stiffer, Y direction is stiffer. Overall, when you look at this as a two, X direction is stiffer, right? Do you see that? Because this is strong axis, right? Than this. Now, when this direction is smaller, but you have a very long core, stiffer, right? But when Y in this case is more bigger because your building width is bigger, but your core wall advance is this one, right? So if you see this as a cube, which one obviously is going to suffer more? Obviously in this direction. More big wind load, you have less stiffness. You can at least observe and at least have some sense general. We're not doing the very advanced technologies. This is just general observation. You already have some sense, right? You play with a Lego block or any wood block, you already know this. Just I try to explain a little bit connection between overall wind and the forces, demand, and your geometry-driven building characteristic and core and associated lateral stiffness. We try to understand. So okay. So again, here displays and response here plot. You could now I'm gonna keep turn on the wind load. I'm just turn. So here, okay. Now overturning moment, story overturning moment. You could right. Take a look at it. You could just summarize this all the forces, right? In your final report, you need to somehow summarize this all the wind loads, shear force diagram from the overturning moment x y direction, right? Consistently, this is the one currently we're looking at the ultimate wind load. 115 miles per hour is ultimate wind speed, basic wind speed. But what we're going to use is, I told you, 50-year wind load for our deflection check. right? Serviceability. So somehow we need to know how to scale down our loading so that we could make service wind load, and then we check our deflection, but we can use it just a load factor. So, but here, so this chart flow chart you can just play around. I'll show you other stuff. But overturning moment, I can show you here the maximum story displacement. So this is this displacement diagram. Under the wind, number one is wind is blowing X direction. It's expecting total deflection, right? I have 5.7 inches, right? This example. I want you to actually run this much, and then next week, I think we're gonna have a workshop, and every team should get this done. So I think watch the video and just work some setting. If you have some time, do some iteration, and if you can get things done, perfect. If you still having problem, next Thursday, let's do some workshop. Bring all the laptop team to work together. And let's conclude this lateral system, so we can move on to next foundation system, right? So here I'm just showing second wind loading 2. Wind is blowing in Y direction. Let's guess what? How much? I have 35 inches deflection here, right? X direction I ETABS calculate 5.7 inches. Now Y direction I have 35 inches. Just assume the total building 600 feet divided by, let's say, criteria 500. I may end up to limit my maximum deflection is 1.5 feet or 16 inches, something like that. But again, this displacement under this wind is ultimate wind load. So what we need to do is we need to, maybe I'll set it up and just, we need to scale down this wind load, is service wind load. Service wind load, service wind. Is for wind load case, we need to scale down by a factor of 0.625 or 0.6. Let's say 0.6. It's 1 divided by 6. 1.6 is the scale factor. 1.6. Let me see it works. The ETABS somehow I need to set up different way. Yeah, it doesn't show this here. I may have to set the load case with. Yeah, here they don't. Oh, here. Okay. Here, service window. Oh, here. I think it show all. So let me see what can you show for you. Service window total have 12 cases. So let's see. Extraction service window is we using 0.6 load factor from scale down from ultimate window to service window. So 0.6 times whatever deflection that ultimate load generate is our service wind deflection. So maybe so hey, here is about 4 inches. 0.6 times 5.7. But still Y direction, I still have 21 inches, which is 0.6 times 35 inches. So